Action.
Hi, I'm Mr. Mack, and I'm going to do a problem for you right now to help explain what optimization is all about. So we're going to do this problem right here, number 2. Well, I probably shouldn't face that way. We're going to do this problem right here, number 2. What is the smallest perimeter for a rectangle whose area is 16 inches squared? So our rectangle has to have an area of 16 inches squared. And what are its dimensions? All right, I'm trying to minimize the perimeter of this rectangle. Now you can think about a lot of different rectangles that have an area of 16, right? Like
16 and 1.
16 and 1, all right. So you could have like a 1 by 16 rectangle, but that's got a perimeter of 34. Maybe that's the smallest perimeter possible of an area of 16. But what if somebody else said it could be
4 and 4.
4 and 4. Ooh, a 4 and 4. If it's a 4 and 4, my perimeter on this one is 16. That's smaller than 34. But what, I mean, you could even make like a super long one, right? It's like a, this is not proportionate, but like a half by like 32, right? Still has an area of 16, but this one has like a perimeter of like, what, like 65? Way too big. I want to minimize my perimeter. Because maybe I'm making it out of like super expensive material or something like that. Okay, so all I gotta do is make an equation. If I can find the bottom of the equation, like the minimum, by setting the slope equal to 0, then I will know by some sort of testing that I'll have a minimum. All right, so here's how these problems go. So I need an equation for a random perimeter of a rectangle. I'll call these sides x and y, okay? And I guess the perimeter, am I fixed on my, what am I fixed on? Area. So my area of my triangle has to be x times y is 16, right? That's a fixed thing. It's going to end up being our helper equation in a minute. But the thing that I'm trying to minimize is my perimeter. And perimeter, of course, perimeter of a rectangle, anybody?
2x plus 2y.
Oh, exactly. Nice job. Okay. Random student who is nameless because we're on video. Perimeter is 2x plus 2y. This is great. The problem is I can't go to like my TI calculator and stick in 2x plus 2y and find the minimum of it because it's got too many letters. Okay. I need to be able
Students that need
to.
a ride to Spokane Valley Tech, please come to the main
All right.
office.
I'm going to go. I'm going to go ahead and do this thing called substitution and get rid of one of the variables so I can find the minimum of it. And usually in something like this, I like to stick with x's because that's a nice variable. So if I go to my helper equation here, I realize that since x times y is 16, y, if I solve this for y,
16 over x.
I get 16 over x. That's nice. So y is 16 over x, which is great. I can then just substitute this right in here, and it's 2x plus 2 of those. So my perimeter now, as desired, becomes this 2x plus 32 over x. This is a really nice single variable x equation, which I can stick in to find the minimum of. But we don't need a calculator to find the minimum of a curve. We know how to do this. Because all I got to do is take the derivative and find when it's equal to 0, and then I can see if it's a min or not. All right, so, one important thing we got to consider is what is x allowed to be? Possible values of x, okay? So what is like the smallest that x could be? Could x be smaller than a half?
Yes.
X could be like
0.0001.
0.0001?
Yeah.
If this was 0.0001 and it kept going forever, this would have to be 16. How many would I need? A bunch of them, right? Hold on. Pop, 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 pop. This is a huge perimeter, right? I don't want a perimeter that long. But x could be super, super teeny. So x could be any number between 0 and, but I could actually, if this was now vertically super, super tall and my y extremely small, x really could be any number between 0 and infinity. It's probably not going to be. It's probably going to be somewhere in one of these, but I'm going to try to figure it out. Okay, so let's try this. So if I take my first derivative, I'm going to get 2, and of course the derivative of 32 over x is, or the derivative of 1 over x is negative 1 over x squared. So the derivative of 32 over x is negative 32 over x squared. And you could do quotient rule right there. You can even do whatever you want. But solving for this now, some people would say I want to do a common denominator, which is okay. do a common denominator. You could add this to both sides. Heck, you can even just realize, isn't 32 divided by 16 2? And I really want this bottom to be 16, and what squares to give 16 is 4. So with any of these, even multiplying across here, x squared equals 16. X can't be 0, which we already knew because we don't want it to be 0. But x could be plus or minus 4. But we can't have x be a negative 4 because the side has to be positive. So x equals 4 is my critical point. So I'm going to do a quick test and make sure I sort of have a floating 0 wall, and it goes out to infinity. But if I take a value, does anybody know a number between 0 and 4? So we give me a number between 0 and 4.
E.
2. Okay. E. 2.
He's better than 2.
E is pretty darn great. I agree. Okay. What's another pretty great number in here?
1.
Yeah.
Pi.
Pi. That's a great one too. All right. Let's go with 2. All right. Thank you. I'm gonna go with 2. Yeah, I'm gonna go with 2. So if I take a 2, but here's my first derivative, right? So if I stick a 2 into here, 2 minus 32 fourths. Well, 32 fourths is 8. 2 minus 8, that's negative. They're like, oh no, that's good, because we want a minimum. So this part goes down. Then if I stick in, anybody got a number bigger than 4?
5.
5. Okay, 6, 5 or 6, either one. But 5 or 6 squared is bigger than 32. No, it's not. 5's not. Oh, but it's okay, because 5 squared is 25. And 32 25ths is a little bit bigger than 1. And 2 minus a little bit bigger than 1 is still positive. But if I put in a 6, 32 36 is smaller than 1, and 2 minus smaller than 1 is positive still. So it doesn't really matter. Hey, look, I found a min. Now let's say you're not about sign testing, and you'd rather do the second derivative test. Nice. Second derivative. That's gone. Ooh. Quotient rule? Maybe pretend that this is 32x to the negative 2. That'd be my way of going. So the derivative of that is, since this is this, I'm just going to take the derivative of that and get positive 64x to the negative 3, which is 64 over x cubed. Okay, now here's the thing. If my first derivative at 4 equals 0, and my second derivative at 4 is concave up, that would be great because that's a min. Well, if you stick a 4 into here, 64 over 4 into here is 64. That's 1. Now, who cares if it's 1 or not? I'm just glad that that's bigger than 0. Because the slope of 0 on a positive concave region means that is a min because of the second derivative test. So we have now proven that the min occurs when x equals 4. But if x equals 4, y is 16 over 4, which is 4. So I can just say, hey, well, or you can just go here. 4 times what is 16? 4. So our dimensions are 4 by 4. Some of you might have said, like, oh, I kind of saw that coming. I think it's going to be a square. So my dimensions are 4 by 4. My minimum smallest perimeter, my minimum perimeter possible is 16. And I'm going to tell you, out of every single possible rectangle that has an area of 16, you will never find one that has a perimeter less than 16.
Never.
And we just proved it using optimization techniques. Bye!
All righty.